The Agreement Machine: How Computers Find Common Ground in a Distributed World. Chapter 1: The Unseen Choreography of Agreement. Imagine the sound of a grand orchestra mid-symphony, a thrilling tapestry of strings, woodwinds, brass, and percussion. Each musician, though playing their individual part, is perfectly synchronized with the others. They listen, they count, they watch the conductor, and they adjust. The result is a harmonious, unified performance. What would happen if, in the middle of a piece, the trumpet player decided to play a different melody, or the violins suddenly sped up while the cellos slowed down? Chaos. Discord. The symphony would collapse into an unbearable noise. This seemingly simple act of 100 musicians agreeing on what note to play, and when, is a powerful analogy for one of the most fundamental yet often invisible challenges in computer science. Consensus. In our daily lives, we constantly seek agreement. A family decides on a vacation destination. A committee votes on a new policy. A group of friends picks a restaurant for dinner. These moments of consensus, sometimes explicit, sometimes unspoken, allow us to coordinate actions, avoid conflict, and move forward with shared understanding. When we fail to agree, things break down. Partnerships dissolve, plans unravel, and progress halts. Now, extend this idea to the digital world. Think of the vast, intricate network of computers that powers our modern existence. Every time you check your bank balance, send a text message, stream a movie, or buy something online, you are interacting with what we call a distributed system. This isn't just one giant computer doing everything. It's a collection of many individual computers, servers, databases, smartphones, cloud instances, all working together, often across vast geographical distances. They are the digital musicians in a planet-spanning orchestra, each playing their part. But unlike human musicians, who can nod, make eye contact, or even shout, "Wait," computers operate independently and blindly. They can't assume another machine is working, or that a message sent will even arrive. Yet, for your bank balance to be correct, for your online order to go through exactly once, or for your favorite streaming service to deliver video without skipping, these independent computer brains must constantly be in perfect agreement. They must silently perform an unseen choreography of coordination. Consider your bank balance. When you check it on your phone, one computer queries a database. When you use an ATM across town, another computer queries, perhaps, a different copy of that same database. If these computers don't agree on your true balance, you might be able to withdraw money you don't have, or worse, find money missing from your account. This is not just inconvenient. It can lead to financial chaos. Or imagine an online store. If multiple servers don't agree on the current stock level of a popular item, two different customers might be told that the last item is available, leading to frustration and refund complexities. The critical insight here is that agreement is not optional. It is the bedrock of trustworthy digital services. Without it, the reliability we've come to expect from our online world would crumble. Data would be inconsistent, transactions would be unreliable, and the very foundation of cloud computing, smart devices, and now, decentralized digital currencies would be impossible. For decades, brilliant minds in computer science have grappled with this profound challenge. How do you get independent, potentially faulty computers to reach a single, ironclad agreement, even when some of them might crash, disconnect, or even behave maliciously? This is the realm of consensus algorithms. These algorithms are the invisible architects that ensure consistency and reliability behind the scenes of every digital interaction. They are the conductors for the unruly orchestra of networked computers, providing the rules, protocols, and mechanisms that allow disparate systems to find common ground, synchronize their actions, and maintain a shared truth. You don't see them working, but you certainly benefit from their flawless operation every single day. Over the coming chapters, we will embark on a fascinating journey to demystify these agreement machines. We'll explore the unique challenges that make agreement so difficult in a distributed world, the fundamental building blocks that these algorithms rely on, the stories behind groundbreaking algorithms like Paxos and Raft, explaining their core ideas simply and intuitively, how these concepts evolved to handle even malicious behavior through Byzantine fault tolerance, the revolutionary role of consensus in the world of blockchain, and decentralized digital ledgers. The myriad of real-world applications where these algorithms are the unsung heroes, from cloud databases to massive internet services. You don't need a computer science degree to understand these powerful ideas. All you need is curiosity and a desire to peer behind the curtain of our digital world. By the end, you'll not only understand how computers agree, but you'll also gain a profound appreciation for the intricate engineering that underpins our interconnected lives. Let's begin the unseen choreography. Chapter 2, The Wild West of Distributed Systems, Challenges to Agreement. In the previous chapter, we explored the idea of agreement as the silent conductor of our digital symphony. We saw how fundamental it is for everything from your bank balance to your cloud storage. But what makes achieving this seemingly simple goal so incredibly difficult for computers? Why can't they just agree like a well-drilled orchestra? The answer lies in the very nature of distributed systems. Imagine, for a moment, moving from a single, unified command center to a vast, lawless frontier. In a single computer, everything is under one roof, controlled by one central brain. Data is local and instantly accessible. Processes communicate directly and reliably. If something goes wrong, the whole machine might crash, but at least you know it's crashed. Now, shatter that single computer into dozens, hundreds, or even thousands of independent machines, scattered across continents, connected only by an unpredictable network. Each machine has its own memory, its own processing power, its own internal clock. There's no single conductor, no central brain overseeing everything. This is the Wild West of distributed computing, a rugged landscape filled with potential pitfalls where reliable agreement is not an inherent feature, but a hard-won victory. Let's unpack some of the fundamental challenges that transform this digital frontier into a difficult territory for consensus. The perils of the network, where messages go to die or get lost delayed. Perhaps the most significant challenge in a distributed system is the unreliability of communication. When computers talk to each other, they don't have a direct, perfect line. They send messages over networks, the internet, local area networks, wireless connections, and these networks are notoriously fickle. Messages can get lost. A network packet containing a vital piece of information might simply vanish. It could be dropped due to congestion, connection breaks, or hardware failure. A computer sends a request, but the recipient never gets it. Did the sender even attempt to send it? Did the recipient process it? Neither machine has definitive proof. Messages can be delayed. Even if a message arrives, there's no guarantee of how long it will take. Network traffic, server load, and geographical distance all contribute to unpredictable delays. A message sent now might arrive before one sent 5 seconds ago. This makes ordering events incredibly complex. Messages can arrive out of order or duplicated. Due to different network paths and retries, a message sent later might arrive earlier, or the same message might arrive multiple times. Imagine if you sent 3 instructions to a friend, but they received them in a different order or got the same instruction twice. Chaos would ensue. This constant uncertainty, the "did you get that? Did you do that? When did you do that?" is the primary source of headaches for designers of distributed systems. Without reliable communication, how can multiple computers ever confidently agree on anything? The unpredictability of machines, the crashing computer. Another harsh reality of the digital Wild West is the inevitability of partial failures. In a single computer, either it works or it doesn't. But in a distributed system, individual components can fail independently while the rest of the system carries on. One server might crash, a hard drive might decide to give up, a memory stick might corrupt, or a network card might fail. The problem isn't just that things break. It's that it's incredibly hard for the other computers in the system to tell why something isn't responding. Has the other server genuinely crashed? Or is it just very, very busy and taking a long time to answer? Is it disconnected from the network? Or perhaps its message just got lost on the way back? This is often called the failure detection problem. Imagine you're part of a team working on a project and suddenly one team member goes silent. Are they okay? Are they just taking a coffee break? Have they quit? You don't know, but you still need to ensure the project gets done, and you can't wait forever to find out. In a computer system, mistakenly marking a busy but alive server as dead can lead to wasted resources or inconsistent data, while assuming a truly dead server is just slow can stall the entire system. The illusion of time, clocks, and coordination. A concept we take for granted in daily life is global, synchronized time. We all agree on what noon means. Not so in a distributed system. Each computer has its own internal clock, and even with sophisticated synchronization protocols, these clocks will inevitably drift slightly. There is no single, universally agreed upon now across a distributed system. This might seem like a minor detail, but it has profound implications, especially when ordering events. If a user tries to withdraw money from their bank account at 10:01 a.m. on one server, and their paycheck is deposited at 10:02 a.m. on another server, which event happened first in a global sense? If the clocks aren't in perfect sync, the apparent order might be reversed, leading to an overdraft or an incorrect balance. Ensuring that all computers agree on the correct sequence of events, despite their drifting clocks, is a tricky problem that consensus algorithms must address. The data dilemma: consistency, availability, and partition tolerance. The challenges outlined above lead to one of the most fundamental dilemmas in distributed systems. It's often summarized by a principle known informally as the CAP theorem, which states that in a distributed system that must tolerate network partitions, i.e., parts of the network breaking off from each other, you can only guarantee 2 out of 3 desirable properties. Consistency: every read receives the most recent write or an error. All copies of the data are identical everywhere. Availability: every request receives a response without guarantee that it is the most recent write. The system is always open for business. Partition tolerance: the system continues to operate even if there are arbitrary communication breaks, partitions, in the network. Since network partitions will happen in real-world systems, they are a fact of life on the internet. You often have to make a painful choice between consistency and availability. Do you prioritize always having the most up-to-date information, even if it means sometimes you can't access parts of the system? Or do you prioritize always being able to respond to requests, even if the data you provide might be slightly out of sync? Different applications make different trade-offs here, based on their needs. What's acceptable for a social media feed might be catastrophic for a banking system. The unsung triumph: why consensus algorithms are heroes. Despite these daunting challenges, unreliable networks, unpredictable machine failures, drifting clocks, and fundamental trade-offs, distributed systems form the backbone of our digital lives. They manage petabytes of data, process millions of transactions per second, and serve billions of users worldwide. They work. They work because our digital orchestrators, the consensus algorithms, are designed precisely to navigate this Wild West. They are the robust rulebooks and clever protocols that allow independent, fallible machines to bypass the chaos and forge a singular, reliable agreement. They don't make the problems disappear, but they provide the intelligent mechanisms to overcome them, ensuring that even in the face of inevitable failure and uncertainty, our digital world remains consistent, reliable, and trustworthy. In the coming chapters, we will dive into these remarkable algorithms, starting with the foundational concepts that enable them to achieve this seemingly impossible feat. Chapter 3: Building Blocks of Certainty. Fundamental concepts. The digital Wild West, as we explored in the last chapter, is a chaotic place. Networks are unreliable, computers fail unexpectedly, and there's no universal clock. Yet somehow, critical systems like banks and cloud storage manage to maintain ironclad agreement. How do they achieve this seemingly impossible feat? The answer lies not in eliminating these problems, but in ingeniously working around them. Consensus algorithms are the clever architects who build sturdy structures on shaky ground. They do this by combining a few fundamental building blocks in brilliant ways. Understanding these core concepts is your key to unlocking the mysteries of how computers find common ground. Building redundancy. The power of replication. Imagine you have a single, super important document. What's the first thing you do to protect it? You make copies, lots of copies. You might keep one in a fireproof safe, one with your lawyer, and another in a cloud service. If one copy is lost or destroyed, you still have others. This simple concept, making copies, is the cornerstone of reliability in distributed systems, and it's called replication. Instead of relying on a single computer, which can always fail, distributed systems run multiple copies, or replicas, of their data or processes across different machines. Why replicate? Availability. If one server goes down, another can immediately take over its duties, ensuring continuous operation. Durability. If data is stored on multiple machines, the chances of losing it due to a single machine failure are drastically reduced. Scalability. Spreading the workload across many machines can handle more requests and process more data. The challenge, however, quickly becomes apparent. How do you keep all these replicas consistent? If you update one copy of your important document, how do you ensure all the other copies reflect that change accurately and promptly? If they get out of sync, the whole point of replication is lost, leading to conflicting truths. This is precisely where the need for consensus algorithms arises, to ensure all replicas agree on the same changes, in the same order, and thus remain consistent. The guiding hand. The role of a leader. While consensus aims for agreement among many, one common pattern to simplify decision-making is to elect a leader. Just as an orchestra needs a conductor, a sports team needs a captain, or a government needs a prime minister, many consensus algorithms designate one particular computer or process to coordinate actions. The leader's role is to propose decisions, marshal operations, and ensure that other replicas follow suit. This approach has significant advantages. Simplification. Instead of every computer trying to make a decision independently, which risks contradictory actions, one central point coordinates. Order. The leader can dictate the order in which operations are processed, which is crucial for consistency. However, the leader introduces a new problem. What happens if the leader itself fails? If the conductor suddenly drops their baton, the orchestra is once again in peril. Robust consensus algorithms must not only agree on a leader, but also have a mechanism to detect if the leader has failed and then gracefully elect a new one. This process is called leader election, and it's a critical component of many such systems. The power of the crowd, voting, and quorums. How does a collection of independent computers reach a collective decision? They vote, but unlike human elections, where every vote counts equally in distributed systems, it's about forming a quorum. A quorum is a minimum number of votes that must be achieved for a decision to be considered valid and committed. It's not necessarily everyone agreeing, but a sufficient majority. The cleverness of a quorum lies in its mathematical property. For any two distinct proposals, it is impossible for both to simultaneously achieve a quorum. Think of it this way. If you have 5 computers, n equals 5, and a quorum requires a strict majority, e.g., 3 votes, which is n2 plus 1, then Proposal A gets 3 votes. Proposal B tries to get 3 votes, but it would need to share at least one computer with Proposal A's voters. This overlap is critical. Any two quorums must intersect, meaning they will share at least one common member. This shared member acts as a memory keeper, able to convey information about past decisions to future quorums. This ensures that once a decision is made and committed by a quorum, it can never be contradicted by a future decision, even if some of the original voting members are now offline. Quorums are the mathematical guarantee of agreement and non-contradiction. The system's autobiography, state and state machines. To understand what computers are agreeing on, we need the concept of state. In computing, the state of a system refers to all the information it currently holds. For your online bank account, its state includes your current balance, recent transactions, and account details. For a game of chess played online, the state is the current position of all the pieces on the board. A state machine is a model where a system progresses from one state to another based on a specific sequence of inputs or commands. If all the copies, replicas of your system start in the identical initial state, and they all apply the exact same sequence of commands in the exact same order, they will all arrive at the exact same final state. This is the ultimate goal of strong consistency, to maintain identical state across all replicas. Consensus algorithms are essentially about getting all the independent computers to agree on the sequence of commands to apply to their respective state machines. Once they agree on this sequence, everything else falls into place like dominoes. The permanent record, the log. How do we ensure all replicas process the same sequence of commands in the same order, especially when messages can be lost or delayed? The solution is to use a log. Imagine a meticulously kept journal or ledger where every single important event, every command, every decision is recorded sequentially. This is what a distributed log is, an ordered, append-only sequence of operations. Each entry in the log is a command or an instruction that, when applied to a system state, changes it in a predictable way. For example, log entry 1. User A deposits $100. Log entry 2. User B withdraws $50. Log entry 3. User A transfers $20 to user C. Consensus algorithms fundamentally work by agreeing on what entries to add to this shared log. Once an entry is committed to the log by a quorum, it is considered permanent, immutable, and replicated across all consistent nodes. All honest participants then process these committed log entries in the exact same order, ensuring they all maintain the identical system state. The log neatly addresses the issue of order and consistency. Even if a message arrives late or out of sequence, its position in the committed log dictates when it is actually processed by the state machine. The do no harm principle. Idempotence. Given the unreliability of networks, a computer might accidentally receive and try to process the same command multiple times. For example, a deposit $100 command might get sent twice. If this happens, your bank balance would be incorrectly inflated. To handle this, many distributed system operations, or the way they are processed, aim for idempotence. An operation is idempotent if executing it multiple times has the same effect as executing it once. Set user A's balance to $200 is idempotent. Running it multiple times will always result in a balance of $200. Add $100 to user A's balance is not idempotent, as running it twice would add $200. While not strictly a consensus algorithm concept, understanding idempotence helps in designing reliable systems that use consensus. Often, consensus algorithms ensure that even if the same message is proposed multiple times, the effect on the logical state, via the log, is only applied once. Laying the foundation. These fundamental ideas, replication for redundancy, leaders for coordination, quorums for robust agreement, state machines to model system changes, and logs to record and order those changes, are the intellectual scaffolding upon which all robust consensus algorithms are built. Different algorithms combine and refine these concepts in elegant and often surprising ways to overcome the inherent challenges of distributed computing. With these building blocks in your mental toolkit, you are now ready to appreciate the ingenuity of specific consensus algorithms. We will start with one of the most intellectually profound, though notoriously complex, algorithms, Paxos. Chapter 4. The Grandmaster's Algorithm, Understanding Paxos. In our journey to understand how computers agree, we've covered the severe challenges of the distributed world and the fundamental building blocks: replication, leadership, quorums, state machines, and logs that systems use to manage them. Now we arrive at what many consider the grandmaster of consensus algorithms, Paxos. Paxos is famous for two reasons: its remarkable power and its legendary complexity. Many computer scientists describe Paxos as elegant, mathematically sound, and incredibly robust. They also often add that it's fiendishly difficult to understand, even harder to implement correctly, and a nightmare to debug. There's even a widely known joke the algorithm's inventor supposedly made. Paxos makes all other consensus algorithms trivial by comparison. The architect behind Paxos is Leslie Lamport, a Turing Award winner and one of the most influential figures in distributed systems research. He published his seminal paper on Paxos in 1990, but due to its unusual, allegorical presentation, set as a story about a fictional ancient Greek parliamentary body on the island of Paxos, it was largely misunderstood and overlooked for years. It took a subsequent, more conventional paper in 1998 titled The Part-Time Parliament to clarify its significance. Why Paxos is the Grandmaster? So what makes Paxos so special and so difficult? Its core brilliance lies in its ability to guarantee agreement and consistency, even when multiple participants fail simultaneously. Messages are lost or network connections flicker. Unlike simpler forms of agreement that might break if a leader crashes, Paxos is designed to withstand a wide range of faults without losing data or making inconsistent decisions. It focuses on safety, never doing anything wrong, over liveness, always making progress, though it strives for both. Think of Paxos as a highly sophisticated multi-party negotiation protocol where the goal is to agree on a single atomic decision, say, the next entry in a shared log. It assumes no single point of failure and operates on the principle that any decision must be agreed upon by a majority or a quorum of participants. The players in the Paxos drama. To understand Paxos, let's simplify its roles, which are often overlapping in real systems. Proposers, these are processes that want to propose a value to be agreed upon. They send messages to try and convince acceptors. Any server can act as a proposer. Acceptors, these processes are the decision makers. They either accept or reject proposals. They are the voting members, and a majority of them accepting a value means that value is chosen. Learners, these processes are interested in what value has been chosen. Once a value is decided by a quorum of acceptors, learners discover it. Crucially, in Paxos, there isn't a single, fixed leader in the traditional sense. While a proposer acts somewhat like a temporary leader for a particular proposal, any server can attempt to become a proposer, and multiple proposers might be active simultaneously. This fluidity is part of what makes Paxos so resilient. The two-phase ballet of agreement. Paxos works through a carefully choreographed, two-phase commitment process for each decree or value it's trying to get agreed upon. Let's imagine our goal is to agree on a specific number, say, 42. Phase 1, the prepare phase seeking a promise. The proposer initiates. A proposer, say, server A, wants to get the value 42 accepted. It first sends a prepare message to a majority of acceptors. This message includes a unique, ever-increasing proposal number, let's call it P1. The higher the number, the more recent the proposal attempt. Acceptors respond and promise. When an acceptor receives a prepare message with proposal number P1, it does two things. It looks at its history. Has it already promised to ignore any proposals older than P1? If P1 is higher than any proposal number it remembers seeing, it enters into a new promise. It replies to the proposer, promising not to accept any future proposals with a number lower than P1. This is a critical promise that prevents older, conflicting proposals from being accepted. Additionally, it sends back any value it has already accepted in the past, along with the proposal number associated with that accepted value. This ensures that a proposer can't just ignore previously accepted values. If the proposer gets responses from a majority, a quorum of acceptors, it moves to the second phase. If any of those responses indicated they had already accepted a value for a higher proposal number than P1, the proposer must adopt the highest numbered accepted value it heard about. This rule ensures that previously decided values are not overwritten, preserving safety. If it didn't hear about any previously accepted values, it can propose its own value, 42. Phase 2. The accept phase, committing the value. The proposer sends the acceptance request. Having gathered responses from a majority and having decided on the final value, either 42 or a previously accepted value it was forced to adopt, the proposer sends an accept message to a majority of acceptors. This message contains the chosen value and the proposal number P1. Acceptors commit or reject. An acceptor, upon receiving an accept message for proposal P1 with the chosen value, will check its promises. Has it already promised to ignore proposals with numbers lower than P1? If P1 is still the highest proposal number it has promised to consider, it records the value as accepted and replies to the proposer. Crucially, if it has since made a promise for a higher proposal number than P1, presumably from a different proposer that has started a newer round, it rejects the proposal. This is why a new round of Paxos might be needed if conflicts arise. If the proposer receives accept responses from a majority, a quorum of acceptors, then the chosen value is considered agreed upon and finalized. At this point, any learner can now discover and apply this value to its local state. The magic of quorums, revisited. The genius of Paxos lies in its rigorous use of quorums in both phases. Suppose a value, say, 42, is accepted by a majority of acceptors in one round. Now imagine a new proposer wants to propose 99. For 99 to be accepted, it also needs to get accepted by a majority of acceptors. Because any two majorities must overlap, they share at least one common acceptor. If 42 was accepted by a majority, then any new majority attempting to agree on 99 will include at least one acceptor who previously accepted 42. This shared acceptor will, in the prepare phase for 99, tell the new proposer that 42 was already accepted. This forces the new proposer to then try to get 42 accepted or a newer subsequent value, rather than proposing 99. This mechanism ensures Paxos never allows two conflicting values to be accepted, guaranteeing its safety property. Paxos in the real world, a theoretical blueprint. Despite its formidable power, directly implementing Paxos is notoriously difficult due to its complexity and the potential for endless loops if proposals frequently collide. This led to Leslie Lamport famously stating, "Paxos is not hard, it is just different." Which is true, it follows a logic that is not intuitive to human thought patterns. Therefore, many real-world systems don't implement pure Paxos. Instead, they either use simplified versions or tamed Paxos. Systems like Google's Chubby Lock service, which is fundamental to many other Google services like Bigtable and GFS, use a master replica approach that simplifies Paxos by having a stable leader, reducing some of the complexity found in the original algorithm. Algorithms inspired by Paxos. Many modern consensus algorithms borrow its core ideas of a multi-phase commitment and quorum-based voting, but they simplify the process, often by enforcing a stronger concept of a single, stable leader. Paxos remains a cornerstone of distributed systems theory. Understanding it provides invaluable insight into the extreme measures required to achieve fault-tolerant consensus in the most adversarial network conditions. Its principles have profoundly influenced the design of many practical distributed systems, even if its direct implementation is rare. However, recognizing its complexity, the community yearned for an algorithm that was equally robust but simpler to understand and implement. This craving gave birth to algorithms like Raft, which we will explore next. Raft takes many of the core ideas of Paxos, but reimagines them with a focus on comprehensibility and ease of use. Chapter 5. Clarity from Complexity, the Raft Consensus Algorithm. After wrestling with the intellectual giants of Paxos, you might feel a bit like a student who has just parsed a complex philosophical text, rewarded by insight, but perhaps a little dazed. Paxos, for all its power and robustness, is undeniably challenging to grasp, and even more so to implement correctly. For years, this complexity was a significant barrier, slowing the adoption of robust consensus in many systems. Enter Raft. Developed by Diego Ongaro and John Ousterhout at Stanford University, Raft was explicitly designed with understandability as its primary goal, alongside correctness and performance. Its motto could well be, "Consensus for the common person and programmer." While its underlying principles are still mathematically rigorous, Raft organizes its logic and reduces the number of distinct states and interactions dramatically, making it far more approachable than Paxos. If Paxos is a grandmaster of chess, able to calculate intricate combinations many moves ahead, Raft is a highly skilled, incredibly disciplined squad leader. It follows clear, well-defined procedures that are easier to visualize and execute, delivering the same fault tolerance with greater clarity. Raft's guiding principle, a strong leader. The most significant philosophical departure Raft makes from Paxos is its unwavering commitment to a strong leader. In Paxos, any server could try to propose a value, and leadership was temporary and fluid. This made it resilient but confusing. Raft simplifies this by making leadership explicit, stable, and central to all operations. At any given moment, there is exactly one leader in a Raft cluster, and all client requests must go through this leader. This design choice significantly streamlines the consensus process. Instead of complex multi-proposer interactions, Raft employs a straightforward chain of command. The leader dictates changes, and the followers obey. Raft's three states of being. Every server in a Raft cluster exists in one of three clear and distinct roles. Follower. This is the default and most common state. Followers are passive. They simply listen for messages from leaders, like appending log entries, or from candidates, like requesting votes. If they don't hear from a leader for a certain period, a timeout, they assume the leader has failed and transition to a candidate state. Candidate, when a follower suspects the leader is gone, it becomes a candidate. Its job is to campaign vigorously to become the new leader. It requests votes from other servers. Leader, the server that wins the election becomes the leader. It is now responsible for handling all client requests, replicating log entries to the followers, and sending periodic heartbeat messages to assure followers that it's still alive and in charge. This clear distinction between roles greatly simplifies understanding system behavior. The election dance, choosing a new leader. Leader election is a critical phase in Raft. When a leader fails, e.g., its server crashes or the network linked to it breaks, its followers stop receiving heartbeats. After a randomized election timeout, the randomization helps prevent split votes if multiple followers time out simultaneously. A follower will increment its term, number, a continuously increasing integer representing a period of leadership and transition into the candidate state. As a candidate, it performs these steps, increments its term, marking the start of a new election period. Votes for itself, naturally, sends request vote messages to all other servers in the cluster. When other servers receive a request vote message, they check the candidate's term. If it's older than their own current term, they reject the vote because there's a newer election happening. They check if they've already voted in this term. They won't vote twice. Crucially, they implement a log completeness check. A server will only vote for a candidate if the candidate's log is at least as up to date as its own. This is a vital safety mechanism, ensuring that elected leaders always have all the committed log entries, preventing data loss. A candidate wins the election if it receives votes from a majority of the servers in the cluster. Once elected, it immediately becomes the leader and starts sending out heartbeats to reaffirm its authority. If no one wins due to split votes, candidates eventually time out and start a new election term, repeating the process until a leader emerges. The heart of Raft, log replication. Once a leader is elected, its main job is to ensure that all changes to the system state are consistently replicated across all followers. This happens via the log, which we discussed in Chapter 3. Here's how log replication works in Raft. Client request. A client sends a request, e.g., add X to my balance, create file Y to the current leader. Append to leader's log. The leader appends this request as a new entry to its own local log. This entry is not yet committed. Replication to followers. The leader then sends append entries messages to all followers, asking them to append this new entry to their logs. These messages also include previous log entries to ensure consistency, acting like a form of self-correction if a follower's log is slightly divergent. Follower response. Followers receive the append entries messages. If they successfully add the entry to their logs, they respond positively to the leader. If their log is inconsistent with the leader's, e.g., missing previous entries that the leader has, the leader will work with them to catch them up by sending missing entries. Commitment. Once the leader receives positive responses from a majority of its followers, it considers the log entry committed. At this point, the leader applies the entry to its internal state machine, e.g., updates the balance, creates the file. Critically, a committed entry is guaranteed to be durable and part of the agreed-upon state. Follower application. In subsequent append entries messages, the leader will tell followers which log entries have been committed. Followers, upon learning an entry is committed, will also apply it to their state machines. This ensures all servers eventually apply the same sequence of committed entries. This process ensures that all servers eventually have identical, consistent logs, even in the face of failures, because the leader acts as the single source of truth for all changes. Raft safety guarantees. Raft provides strong safety guarantees, ensuring that it never makes incorrect decisions. Election safety. At most, one leader can be elected in a given term. Leader completeness. If a log entry has been committed in a given term, then any leader for subsequent terms must have that entry in its log. This is the crucial part that ensures data integrity. Because only candidates with the most complete logs can win elections, no committed data will ever be lost or overwritten by a less-informed leader. Log matching. If two logs contain an entry with the same index and term, then the logs are identical up to that entry. This simplifies how leaders bring followers up to date. Raft also includes mechanisms for dynamic cluster membership changes, adding or removing servers, and log compaction, snapshots to keep log sizes manageable, further showcasing its practical design. The triumph of understandability. While Raft certainly involves thoughtful design, its elegance lies in structuring the consensus problem into more manageable, intuitive subproblems. Leader election, log replication, and safety. This deliberate focus on understandability has made Raft incredibly popular in recent years, leading to numerous open-source implementations and its adoption in a wide array of distributed systems, from cloud databases like Etcetera and Console to distributed queue systems and even blockchain-related projects that prioritize clarity and ease of implementation over the theoretical minimums often explored in Paxos. Raft demonstrates that it's possible to build robust, fault-tolerant consensus algorithms that are not only powerful, but also accessible to a broader audience of engineers and architects. It's a testament to the idea that clarity can be a powerful design principle, even for the most complex problems. But what if the failures aren't just accidental crashes or network hiccups? What if some of the participants in our distributed system are actively trying to deceive, corrupt, or sabotage the agreement process? This introduces an even more challenging frontier: Byzantine fault tolerance, which we will explore next. Chapter 6, Beyond Crashes, Surviving Malice with Byzantine Fault Tolerance. We've journeyed from the fundamental need for agreement to the challenges of network unreliability and machine crashes. We've seen how algorithms like Paxos and Raft brilliantly manage these fail-stop, where a machine simply stops responding, or fail-recover, where it eventually comes back online, types of failures. These algorithms assume that if a computer isn't behaving correctly, it's because it's faulty, it's broken, slow, or disconnected, but certainly not malicious. But what if the problem isn't just an accidental crash? What if some of the participants in our distributed system are not just broken, but actively lying, sending conflicting information, making misleading promises, or deliberately trying to sabotage the system? This brings us to a far more challenging frontier: Byzantine fault tolerance, BFT. The problem of the traitorous machine. The term Byzantine comes from a classic thought experiment formulated by Leslie Lamport, Robert Shostak, and Marshall Pease in 1982, aptly named the Byzantine generals problem. It perfectly illustrates the core challenge of BFT: how to reach consensus when some participants might be traitors. Imagine an army of several divisions, each commanded by a general. These divisions are encamped around an enemy city. To succeed, they must all attack simultaneously or all retreat simultaneously. If some attack and others retreat, they will be defeated. The generals communicate with each other only by sending messengers. Here's the catch: one or more of these generals might be a traitor. A traitor general could send one message to General A, ordering an attack, and a different message to General B, ordering a retreat. If any division receives conflicting orders, chaos ensues. If the leader general is a traitor, they could send out false orders, and loyal generals wouldn't know if the order they received was the true order or a malicious one. The goal is to devise a strategy that guarantees all loyal generals will agree on a common plan, either attack or retreat, even if there are traitors among them, and even if some messengers get lost or compromised. This requires an incredibly robust form of consensus. Why Byzantine faults are so much harder. In the world of crash failures, a faulty computer is simply absent or silent. It's like a musician who stops playing. You know they're not contributing, and you can work around their absence by relying on others. A Byzantine fault, however, is like a musician who suddenly starts playing the wrong notes at the wrong tempo or randomly shouting contradictory instructions. They are actively poisoning the well of communication and consensus. This makes reliable agreement exponentially more difficult because you can't trust the information you receive, even if it comes from a supposedly live participant. To overcome this, BFT algorithms must operate under the darkest assumptions. A faulty node can send different information to different nodes. It can refuse to send information. It can forge messages. It can act in any arbitrary, self-serving, or malicious way imaginable. The principles of Byzantine fault tolerance. Given such a hostile environment, BFT algorithms rely on a set of core principles that go beyond simple replication and majority rule. Extreme redundancy. You need significantly more honest participants than malicious ones. The classic BFT result from the Byzantine generals' paper states that to reach agreement in the presence of F faulty generals, or nodes, you need a minimum of 3 F plus 1 total generals. So, if you have one traitor, you need at least 4 generals, 1 traitor plus 3 honest, to ensure agreement. This means a minimum of 2/3 of the participants must be honest and able to communicate. This greatly increases the resource cost. Multi-phase communication. A simple 2-phase commit is not enough. BFT protocols typically involve multiple rounds of communication. This extensive back and forth ensures that every honest node receives enough information from enough sources to detect and disregard malicious behavior. It's like having every general double-check every order with every other general multiple times, often requiring digital signatures to prove a message's origin. Cryptographic proofs. How do you know a message actually came from the general who signed it and that it hasn't been tampered with? Digital signatures, often using public key cryptography, are essential. Every message is cryptographically signed, allowing recipients to verify authenticity and integrity. This prevents malicious nodes from forging messages or altering them in transit without detection. Deterministic agreement. Unlike some probabilistic consensus mechanisms, classical BFT algorithms aim for deterministic agreement. Once a decision is made, it is final and irrevocable. Practical Byzantine fault tolerance, PBFT. While the Byzantine generals' problem defined the challenge, it wasn't until 1999 that Miguel Castro and Barbara Liskov introduced practical Byzantine fault tolerance, PBFT. This was a groundbreaking algorithm that made BFT feasible for real-world systems. PBFT works by having a designated primary node similar to a leader that proposes operations. The other nodes are backups. The protocol proceeds through several phases, involving messages exchanged between the primary and backups, and crucially, all messages are cryptographically signed. In simplified terms, PBFT goes something like this. Client request. A client sends a request to the primary node. Pre-prepare. The primary assigns a sequence number to the request and multicasts it to all backup nodes. Prepare. Backups verify the request and multicasts a prepare message to all other nodes, including the primary. Each node collects prepare messages for the request. Commit. Once a node gathers 2 F plus 1 matching prepare messages, where F is the maximum number of faulty nodes, it multicasts a commit message to all other nodes. Reply. Once a node gathers 2 F plus 1 matching commit messages, it executes the request and sends a reply to the client. The 2F plus 1 threshold at each stage ensures that even if F nodes are malicious, there will always be a majority of honest nodes confirming the message, allowing correct nodes to agree on the order and execution of operations. If the primary node fails or acts maliciously, a view change protocol is initiated to elect a new primary. PBFT demonstrated that BFT could be achieved with a relatively efficient, though still more complex than Paxos, communication pattern, paving the way for its use in various specialized applications. Where BFT matters. Historically, BFT was of interest primarily to very high-stakes, mission-critical systems where absolute reliability and security were paramount, such as aircraft control systems, where a single malfunction could be catastrophic, nuclear power plant control, ensuring sensors and actuators always operate correctly, spacecraft operations, where manual intervention is impossible. However, in the 21st century, the need for BFT exploded with the advent of blockchain technology and decentralized ledger systems. For the first time, computers needed to agree on a shared truth even when the participants were completely untrusted, anonymous, and diverse, operating in different economic contexts. How do you ensure no single entity can cheat, double spend, or corrupt the entire ledger? The answer lies in BFT. While most large public blockchains like Bitcoin and Ethereum don't use classical PBFT directly due to scalability limitations with a large, unknown number of participants, they employ a variant of Byzantine fault tolerance known as Nakamoto consensus. This mechanism, underpinned by proof of work, or proof of stake, allows a massive, open network of pseudonymous participants to agree on the state of a shared ledger, robustly defending against malicious actors while not relying on a fixed, known set of participants. BFT algorithms are the ultimate guardians of digital integrity, ensuring that agreement can be forged even in the most adversarial environments. They are the cryptographic fortresses that allow systems to operate securely and reliably, even when faced with deliberately deceptive behavior. In the next chapter, we will delve deeper into how these principles manifest in the revolutionary world of blockchain. Chapter 7, The Ledger of Trust, Consensus in Blockchain. Our exploration of consensus algorithms has so far navigated the complexities of getting a known, relatively stable group of computers to agree on a shared truth, even when their parts might fail. We've seen how Paxos and Raft achieve this in closed, controlled environments like data centers. But what if the participants aren't known, aren't necessarily trustable even if they're not explicitly malicious in the traditional sense, and can join or leave the network at will? What if the very essence of the system is to operate without a central authority? This is where the revolutionary idea of blockchain technology enters the stage, and with it, a renewed and highly visible focus on Byzantine fault tolerance. At its core, a blockchain is a distributed, immutable ledger. Imagine a shared digital notebook where every page, a block, is filled with transactions or data. Once a page is filled and added to the notebook, it's sealed and chained to the previous page using cryptography, making it virtually impossible to alter any past entry without invalidating the entire chain that follows. Crucially, everyone on the network has their own copy of this entire notebook, and they all need to agree on what new page to add next to keep everyone's copy identical. The genesis of digital trust. Bitcoin and Nakamoto consensus. Before blockchain, the biggest hurdle for digital currencies was the double spending problem. If I have a digital token, what prevents me from sending it to you, and then sending the exact same token to someone else moments later? In a centralized system, a bank's ledger prevents this. In a decentralized world, where there's no bank, how do we prevent this fraud? In 2008, an anonymous entity known as Satoshi Nakamoto solved this with the invention of Bitcoin, introducing a groundbreaking consensus mechanism called Nakamoto consensus, primarily implemented via proof of work, POW. This was the first practical solution to achieving Byzantine fault tolerance in an open, permissionless, and truly decentralized network with no central coordinator. Here's how it works. Transactions broadcast. When you want to send Bitcoin, you broadcast your transaction to the network. Every node receives it and verifies its validity, e.g., you have enough funds, your signature is correct. The mining race, proof of work. Nodes called miners collect these valid, unconfirmed transactions into a candidate block. To add this block to the chain, a miner must solve a computationally intensive cryptographic puzzle, the proof of work. This puzzle involves finding a specific number, a nonce, that, when combined with the block's data and run through a cryptographic hash function, produces a result that starts with a certain number of zeros. It's essentially a guessing game that requires a lot of computational power and time to solve, but is very easy for anyone else to verify once a solution is found. Victory and broadcast. The first miner to find a valid solution broadcasts their newly mined block to the entire network. Verification and appending. Other nodes receive this block. They quickly verify, the transactions are valid. The proof of work puzzle was indeed solved correctly. If all checks pass, they accept the block and append it to their copy of the blockchain. The longest chain rule. This is the core consensus rule. In case of a temporary conflict, e.g., two miners solve the puzzle at roughly the same time, leading to two valid branches, nodes will always continue building on the longest chain they see. The longest chain is the one that has had the most computational work, i.e., proof of work, expended on it. Eventually, one branch will become significantly longer, and the shorter branch will be abandoned and its transactions re-added to the pool. How Nakamoto consensus achieves Byzantine fault tolerance. Nakamoto consensus doesn't rely on 2f+1 known, honest nodes like PBFT. Instead, it ingeniously leverages economic incentives and the immense computational cost of the proof-of-work puzzle to achieve consensus in an open network where participants might be anonymous and self-interested. Byzantine. Honest motivation. Miners are rewarded with new cryptocurrency and transaction fees for successfully adding a block. Their self-interest aligns with honest behavior because they only get paid if their block is valid and becomes part of the longest chain. Invalid blocks are rejected, and the computational effort spent on them is wasted. Cost of attack. To consistently defraud the system, e.g., double spend, rewrite history, a malicious actor would need to control more than 50% of the total computing power of the entire network. This is known as a 51% attack. If a malicious actor controls less than 50%, the honest miners, who collectively control the majority of computing power, will always be able to build a longer, valid chain faster than the attacker, nullifying the attacker's efforts. The sheer scale of computational power, known as hash rate, in networks like Bitcoin makes a 51% attack incredibly expensive and practically infeasible. Probabilistic finality. Unlike deterministic BFT algorithms, transactions in Bitcoin reach probabilistic finality. This means that as more blocks are added on top of a transactions block, the probability of that transaction being reversed becomes astronomically small. After 6 confirmations, 6 blocks built on top, a transaction is generally considered irreversible. Bitcoin's consensus mechanism effectively transforms the problem of trust into a problem of verifiable computational work. It creates a trustless environment where participants don't need to inherently trust each other, but rather trust the cryptographic and economic rules of the system. Trade-offs and the evolution of blockchain consensus. While proof of work is incredibly robust and secure, it does come with significant trade-offs. Energy consumption. The computational effort required is enormous, leading to high energy usage, which is a major environmental concern. Scalability. The time it takes to produce new blocks, e.g., every 10 minutes for Bitcoin, every 15 seconds for Ethereum pre-merge, limits the number of transactions per second the network can handle, leading to congestion and higher fees. These limitations have led to the exploration and implementation of alternative consensus mechanisms, most notably proof-of-stake (PoS). In PoS, instead of competing with computational power, validators lock up a certain amount of the cryptocurrency as collateral. The probability of being chosen to create the next block and earn rewards is proportional to the amount of currency staked. If a validator misbehaves, their stake can be slashed, partially or fully forfeited. PoS aims to achieve similar security guarantees to PoW, but with significantly less energy consumption and often higher transaction throughput. Ethereum, the second largest blockchain, successfully transitioned from proof-of-work to proof-of-stake in 2022, demonstrating the viability of this approach. Other consensus variations also exist, such as delegated proof-of-stake, DPoS, where token holders elect a smaller group of delegates to validate blocks, offering even higher scalability but potentially more centralization. Some enterprise blockchains use modified PBFT-like algorithms designed for known, permissioned sets of participants. Regardless of the specific mechanism, the underlying challenge remains the same: how to forge a single, consistent, and immutable shared truth among a decentralized group of computers, especially when some might be unreliable or even malicious. Blockchain technology has not only solved this problem for digital currency, but has also opened up new possibilities for decentralized applications that rely on a shared, trustable ledger. From the tightly controlled environments of cloud computing to the wild, open plains of global cryptocurrencies, consensus algorithms are the secret sauce ensuring our digital world remains coherent, reliable, and trustworthy. In the next chapter, we'll explore some of the real-world applications where these sophisticated agreement machines are silently working behind the scenes, making our modern lives possible. Chapter 8: Agreement in Action. Real-world Applications and Implementations. We've delved into the challenges of distributed systems and explored the ingenious mechanisms of consensus algorithms like Paxos, Raft, and Byzantine fault tolerance. These might seem like abstract concepts, buried deep within computer science papers. However, consensus isn't just theory. It's the invisible backbone of nearly every digital service you interact with daily. It's what ensures your photos are reliably stored in the cloud, your online transactions are correctly processed, and your favorite streaming service never loses track of where you paused your show. Let's pull back the curtain and see these agreement machines in action across various corners of our digital world. The cloud, Google's empire built on consensus. Perhaps no company epitomizes the practical application of distributed consensus better than Google. Their entire operation, from search to Gmail to YouTube, runs on a vast, interconnected network of custom-built distributed systems. At the heart of Google's internal infrastructure lies a service called Chubby. While not a global consensus algorithm itself, Chubby is a distributed lock service that relies heavily on a Paxos-like algorithm to maintain its own consistent state. Think of Chubby as Google's digital traffic cop. Other Google services use it to elect their own leaders, to store small but critical configuration data, and to coordinate access to shared resources. If you're using a Google product, chances are you're indirectly interacting with Chubby's Paxos-driven consensus. Beyond Chubby, Google developed Spanner, a globally distributed database that offers strong consistency across continents, meaning it maintains a singular, consistent view of data for all users, everywhere, all the time. Spanner achieves this phenomenal feat by combining GPS and atomic clocks to synchronize time across its data centers, a concept called true time, and then leveraging Paxos to agree on the order of transactions and replicate data across its global network. When you search for something on Google, the speed and accuracy with which results are pulled from geographically dispersed data centers are testaments to consensus in action. Open source pillars, Zookeeper, etc., and Console. Google's innovations inspired a wave of open source projects that bring similar distributed coordination capabilities to the wider world. These tools have become indispensable for managing modern, large-scale applications, especially those built using the microservices architecture movement. Apache Zookeeper. This project, heavily inspired by Google's Chubby, is a centralized service for maintaining configuration information, naming, providing distributed synchronization, and offering group services. It uses an algorithm called ZAB, Zookeeper Atomic Broadcast, which is very similar in principle to Paxos, to ensure that all its replicas maintain a consistent, shared view of the data. Many widely used big data processing frameworks like Apache Kafka and Hadoop depend on Zookeeper for crucial coordination tasks like leader election and service discovery. Etc. Developed by CoreOS, now part of Red Hat, Etc., pronounced etcd, is a highly available key-value store used to store critical data in distributed systems. It's best known as a fundamental component of Kubernetes, the leading platform for automating deployment, scaling, and management of containerized applications. Etc. relies on the Raft consensus algorithm to ensure that all Kubernetes components, scattered across many machines, agree on the desired state of the cluster. Without Etcetera's Raft-powered consistency, Kubernetes couldn't orchestrate complex applications reliably. Console. From HashiCorp, Console is another service popular for service discovery, configuration, and orchestration. Like Etc., Console also leverages the Raft consensus algorithm to maintain its distributed state. It helps different parts of a complex application find and communicate with each other, handling network failures and service restarts seamlessly through its robust consensus mechanisms. These services are the unsung heroes of cloud infrastructure, quietly ensuring that the thousands of individual software components that make up a large application remain synchronized and functional. Messaging and streaming. Apache Kafka. Imagine a massive, real-time fire hose of data flowing through a company, user clicks, sensor readings, financial transactions. How do you ensure that all these messages are delivered reliably, in the correct order, and processed exactly once, across a system engineered for high throughput and fault tolerance? Apache Kafka is a distributed streaming platform designed for exactly this. It's used by companies like LinkedIn, its birthplace, Netflix, Uber, and many others to handle billions of events per day. While Kafka's core message queues are optimized for speed, its consistency guarantees depend on robust consensus. Early versions of Kafka relied on Zookeeper to manage its broker leadership, which Kafka partition is led by which server and metadata. Newer versions of Kafka are moving towards a self-managed metadata quorum, building consensus directly into Kafka brokers using a raft-like algorithm called kraft. This ensures that even if individual Kafka servers fail, the system can seamlessly elect new leaders for its message partitions, ensuring continuous, consistent data flow. High availability clusters and databases. Beyond the megascale of the internet, consensus algorithms are vital in smaller, more critical settings too. Database management systems. Modern distributed databases like CockroachDB and TDB are designed to be planet-scale and cloud-native, offering strong consistency and high availability. Both extensively use the raft consensus algorithm, or a very close variant, to replicate data across multiple nodes. This ensures that even if one server goes down, the database remains online and all its data is consistent, available, and correct. It's how your favorite online shop ensures your payment goes through, the inventory is updated, and your order is recorded exactly once. High availability clusters. For critical applications, e.g., enterprise resource planning, large financial systems, companies often deploy them on high availability clusters. These are groups of servers designed to provide continuous uptime. If one server fails, another immediately takes over. The magic behind this smooth transition? Distributed consensus. These clusters use algorithms to agree on which server is active, manage shared resources without conflict, and prevent split-brain scenarios, where two servers erroneously think they are the primary, leading to data corruption. The blockchain revolution, a new frontier of agreement. As explored in Chapter 7, blockchain technology represents a powerful new application of consensus, moving beyond known, centralized groups to entirely untrusted, decentralized networks. Public blockchains, Bitcoin, Ethereum, fundamentally use Nakamoto consensus, proof of work, and later proof of stake to allow millions of anonymous participants to collectively agree on the state of a shared, immutable ledger. Every valid transaction, every created block, is the result of a globally distributed consensus process. This revolutionized digital currency and opened the door to decentralized applications, dApps, that operate without a central authority. Enterprise blockchains, Hyperledger Fabric, Corda. While public blockchains prioritize openness, enterprise blockchains focus on permission networks used by businesses. They often employ consensus algorithms directly derived from PBFT, practical Byzantine fault tolerance, or similar leader-based protocols to achieve high transaction throughput and immediate finality among a known set of participants. This facilitates secure, transparent collaboration between organizations without needing a single, trusted intermediary. The silent choreographers. From managing the world's most popular search engine to powering your cryptocurrency transactions, consensus algorithms are everywhere. They are the silent choreographers, working tirelessly behind the scenes to ensure that the vast, complex, and inherently unreliable world of distributed computing can still behave as one coherent, reliable entity. You may not see them, but their flawless operation is the bedrock of our digital lives. They stand as a testament to human ingenuity in solving some of the most profound challenges of fault-tolerant computing. But the quest for perfect agreement is never truly over. New challenges and trade-offs are constantly emerging, pushing the boundaries of what these agreement machines can achieve, which we'll briefly explore in our next chapter. Chapter 9, The Frontiers of Agreement, Challenges and Future Directions. Our journey through the world of consensus algorithms has unveiled the incredible ingenuity born from the necessity of coordinating independent computers. We've seen how Paxos and Raft solidify agreement in the face of machine crashes and network glitches, and how Byzantine fault tolerance tackles outright malevolence. We've explored how these concepts underpin everything from our cloud storage to global cryptocurrencies. Yet, despite these impressive achievements, the quest for perfect agreement is far from over. The landscape of computing is constantly evolving, presenting new scale, security, and efficiency challenges that push the boundaries of existing consensus algorithms. The frontier of agreement is expanding, and with it, exciting new research and practical innovations. Scaling the summits, the blockchain trilemma, and beyond. While public blockchains like Bitcoin and Ethereum demonstrated the power of decentralized Byzantine fault tolerance, they quickly highlighted a core limitation often referred to as the blockchain trilemma. This theory suggests that a decentralized system can optimize for only two of three properties at any given time. Decentralization: how many independent participants can validate transactions and maintain the network. The more participants, the more resilient against central control. Security: how resistant is the network to attacks and manipulation? Scalability: how many transactions per second can the network process, and how quickly can it confirm them? Bitcoin and early Ethereum prioritized decentralization and security, but at the cost of scalability. Their throughput, transactions per second, is relatively low compared to traditional payment networks like Visa. This has led to the development of several strategies to overcome this bottleneck. Sharding: imagine a blockchain as a single, busy highway. Sharding is like building multiple parallel highways, called shards, alongside it. Each shard can process its own set of transactions independently, dramatically increasing the total throughput of the network. A central main chain often coordinates between these shards. Ethereum's significant upgrade to proof-of-stake, the merge, is a foundational step towards implementing sharding in its network. Layer 2 solutions: these are protocols built on top of an existing blockchain, Layer 1, to handle transactions off the main chain, significantly reducing congestion. Examples include Lightning Network for Bitcoin. This creates payment channels between users that can handle many small, fast transactions off-chain, only settling the net result onto the main blockchain. Rollups for Ethereum. These bundle hundreds or thousands of transactions off-chain, compute their collective result, and then submit a single, compressed proof of these transactions to the main chain. This vastly increases transaction capacity. Optimistic rollups and zero-knowledge (ZK) rollups are leading examples. Greener pastures, energy consumption. Proof-of-work (POW), while highly secure, consumes an immense amount of energy due to the computational race among miners. This environmental impact has catalyzed a major shift towards more energy-efficient consensus mechanisms. Proof-of-stake (POS). As discussed, POS replaces computational work with cryptoeconomic incentives, where validators risk their staked cryptocurrency to secure the network. Ethereum's successful transition dramatically reduced its energy footprint, demonstrating the viability of this approach for large, public blockchains. Next-generation POS variants. Research continues on optimizing POS, including different methods for selecting validators, managing stake, and achieving faster finality, often incorporating elements of traditional BFT for greater determinism. The privacy conundrum. Public blockchains by design are transparent. Every transaction is publicly viewable. While this fosters trust, it's a significant barrier for applications requiring confidentiality, such as corporate supply chains, sensitive medical data, or private financial transactions. Future consensus mechanisms are exploring ways to layer privacy on top of transparent ledgers. Zero-knowledge proofs (ZKPs). These cryptographic techniques allow one party to prove they know a piece of information without revealing the information itself. ZKPs are becoming central to privacy-enhancing Layer 2 solutions and could eventually be integrated into consensus protocols. Homomorphic encryption. This allows computations to be performed on encrypted data without decrypting it, offering another path to privacy-preserving operations within a distributed consensus environment. Beyond the block. New data structures. The blockchain model of a linear chain of blocks is elegant, but can limit parallelism. Researchers are exploring alternative data structures for organizing transactions, often based on directed acyclic graphs (DAGs). DAG-based consensus. Instead of a single chain, transactions in a DAG are interlinked in a web-like structure. This allows for parallel processing of transactions, potentially leading to much higher throughput. Projects like IOTA and Nano use DAGs. Their consensus mechanisms differ from traditional blockchains, often relying on nodes confirming a certain number of previous transactions to validate new ones. While promising for scalability, they often face different challenges related to security and achieving global agreement compared to linear blockchains. Quantum threats and post-quantum consensus. The advent of quantum computing poses a long-term, existential threat to many of today's cryptographic algorithms, including those underpinning digital signatures and hash functions used in consensus protocols. A sufficiently powerful quantum computer could, in theory, break current encryption standards, potentially compromising the integrity of cryptocurrencies and other distributed systems. Quantum-safe cryptography. Research is intensely focused on developing, post-quantum, cryptographic algorithms that are resistant to attacks from quantum computers. Future consensus algorithms will need to integrate these new cryptographic primitives to ensure long-term security. The field of Byzantine fault tolerance is also concerned with how to maintain its guarantees in a post-quantum world. The enduring quest. The ongoing evolution of consensus algorithms reflects a fundamental truth. The digital world is dynamic. As networks grow, as new applications emerge from decentralized finance to the Internet of Things at the edge of the network, and as the demands for speed, security, and privacy intensify, the agreement machine must adapt. There will never be a single, universally solved consensus algorithm. The choice of algorithm will always depend on the specific context and the trade-offs one is willing to make, balancing consistency, availability, partition tolerance, security, decentralization, and scalability. Complex systems often employ hybrid approaches, using different consensus mechanisms for different layers or components to achieve optimal performance and resilience. The journey to achieve agreement among independent and often unreliable computational entities is one of the most profound and persistent intellectual challenges in computer science. It is a quest that continues to drive innovation, pushing the boundaries of what distributed systems can achieve, quietly ensuring the reliability and trustworthiness of our ever-expanding digital world. Chapter 10. The enduring quest for certainty. We began this journey by imagining an orchestra, a symphony striving for perfect harmony. We saw how crucial agreement is in our human lives, allowing us to build, cooperate, and coordinate. Then, we plunged into the challenging world of distributed systems and discovered that for computers, achieving agreement is anything but natural. It's a hard-won victory against the unreliability of networks, the unpredictability of machine failures, and even the potential for malicious behavior. The core message woven throughout these chapters is that consensus algorithms are the invisible choreographers of our digital world. They are the fundamental tools that allow disparate, independent machines to forge a single, ironclad truth, ensuring that your bank balance is always correct, that your cloud files are never lost, and that your online purchases are processed exactly once. We mapped the treacherous landscape of distributed computing in the Wild West, understanding that challenges like message loss, arbitrary delays, and partial failures aren't bugs but inherent features. From there, we identified the ingenious building blocks of certainty. The power of replication for redundancy, the role of a leader for coordination, the mathematical magic of quorums for robust decision-making, the elegant simplicity of state machines, and the immutable record of the log. These concepts are the bedrock upon which sophisticated agreement machines are built. Then, we met some of the grand architects. We tiptoed through the elegant but complex corridors of Paxos, Leslie Lamport's Grandmaster's algorithm, a testament to theoretical robustness in the face of profound adversity. We then found clarity and practical applicability in Raft, the algorithm designed for understandability, demonstrating that simplicity can be just as powerful as complexity. The stakes grew even higher as we delved into Byzantine fault tolerance, confronting the uncomfortable truth that not all failures are accidental. When participants can actively deceive or conspire, consensus requires even more rigorous communication and cryptographic guarantees, as exemplified by algorithms like PBFT. This profound challenge found an unexpected, revolutionary application in blockchain technology, where the need for trustless agreement among anonymous participants led to the innovation of Nakamoto consensus, powered by proof of work and its greener successor, proof of stake. Finally, we explored agreement in action, seeing these algorithms silently orchestrating the services that shape our daily lives. From Google's globally distributed systems relying on Paxos, to Kubernetes and cloud databases leveraging Raft through Etcetera and Zookeeper, to the very foundation of digital currencies, consensus algorithms are the unsung heroes operating tirelessly behind the scenes. Our journey concluded by looking to the frontiers of agreement, recognizing that the quest for certainty is ongoing. The demands of ever-increasing scale, the pursuit of greater energy efficiency, the need for enhanced privacy, and the long-term threat of quantum computing all push mathematicians and computer scientists to refine existing algorithms and invent new ones. The blockchain trilemma continues to drive innovation in sharding and Layer 2 solutions, while new paradigms like DAGs challenge the very structure of distributed ledgers. Ultimately, the story of consensus algorithms is a testament to human ingenuity. It's about taking a seemingly impossible problem. How do you get independent, fallible, and sometimes malicious entities to agree on a shared truth in an unreliable environment, and breaking it down into manageable, solvable components? It's about designing protocols that don't eliminate uncertainty, but rather embrace it, building resilience through redundancy, clever rules, and mathematical guarantees. The next time you check your bank balance, upload a photo to the cloud, or make a cryptocurrency transaction, take a moment to appreciate the unseen choreography happening behind the glass. Thousands, perhaps millions, of separate computers are diligently working together, constantly achieving and maintaining agreement, performing a precise, intricate dance. They are the agreement machines, tirelessly bringing order and certainty to our vast, interconnected, and increasingly distributed world. Their work ensures that our digital symphony continues to play in perfect harmony, note after reliable note.